Yeah, I think the mic is fine. Yeah, we're gonna be looking at the methods of proofs. In this section, if you can see, they say that in this section we discuss some of common methods of proof, or some of the common methods of proofs, and the standard terminologies that accompany them. So the terminologies, which are engines, a definition, undefined terms. So when we come to an engine, we should always note that an engine is a statement that is assumed to be true. If we're given a certain statement, you should always assume that it is true. It's like if a person says, it is raining outside. They are true unless you go and prove them wrong, unless you go outside and check that is it raining or not. Then if it is not raining, that means that you would now disprove, right? That's why when we come to methods of proofs, we'll also learn of what we call counterexample, where you need to disprove. So counterexample is just a proof of disproving, right? Or a way of disproving. Now, when it comes to a definition, they say that a definition is used to create new concepts in terms of existing ones. Now we come to a theorem. They say that a theorem is a proposition that has been proven to be true. And a lemma is a theorem that is usually not interesting in its own right, but is useful in proving another theorem. So we'll see which ones are lemmas and how do we go about lemmas. But in most cases, in your standards, we don't focus on lemmas and theorems. So we can come to, they say that a corollary is a theorem that follows quickly from a theorem. So when we come to methods of proofs are divided into three. We have what we call first direct proof, we have indirect proof, and we have proof by cases. So these two, let me use the right one. These two are approached the same way. The only difference there is that this one includes more than one case. You see that this one includes one case. This one includes more than one case. So these two you must keep in mind that they're gonna be approached the same way always. When we come to indirect proofs, it's where we get to differ, or where things differ. Because when we look at the proof by contradiction, a proof by contradiction says that if I'm given P implies Q, I'm going to prove this to say that I'm going to keep the hypothesis and negate the conclusion. You see, right? This will be your assumption. You're going to assume this. When we come to contrapositive, they say that if I'm given P implies Q, this will be logically equivalent to negation of Q implies negation of P. You see, right? Then when we come to a counterexample, that's what we'll talk about disproving. If they give you a certain theorem, how do I disprove it? And so on. All right? So that's what we need to know. Now, let me do this. I think I need to give someone something here. So now when you come to counterexample, that's why you'll see we're gonna be using some examples. Let's say if you are given P implies Q, you're going to let these be certain numbers and so on for you to disprove. But we'll see how do we do that. It will depend on the examples that we're provided with. So let me do this. All right. So when we come to direct proof, here we say that they say that another method, or another important method of proof of great importance in mathematics is proof by mathematical induction, which we will reserve for the upcoming chapters, which this is going to be one of the upcoming chapters, right? Mathematical induction, where we're going to be dealing with proving also. So yeah, I'll be back now. Yeah, so when we come here, we are given these definitions, right? The first definition, they say we should pay attention to this definition, right? This is what we're going to be using most of the times. They say that definition 1.7.1, they say that an integer n is even. Let's check here. An integer n is even. N is even if there exists an integer k, you see right now, such that n is equal to k. They should have said somewhere here, for some, this is very important, these words which I'm writing are very important, for some k element of an integer. So we should keep this in mind. This one, we can skip it for now. It's not that important in this chapter. It will be important in the next chapter, set theory. So now we say that an integer is odd. An integer n is odd if there exists an integer k such that n is equal to 2k plus 1. You see, for an even integer, we talk about n being equal to 2k, and for an odd integer, we talk about n being equal to k plus 1. So also this is not that important for the case. Now we'll talk about it when we come to set theory. So we come to direct proof. Remember, with direct proof, this is just a direct method of proving. This is what you're going to be doing most of the time when you're proving something. They say that in order to prove a conditional statement, remember, we know what is a conditional statement. A statement that has a hypothesis, and also a conclusion. You say right now, we have which has a hypothesis and a conclusion. And they say that we assume P and then deduce Q. Keep this in mind. Most of the times they're going to say something like this: we assume this and deduce this. This, you are not going to write it when you're proving. You say right now, we just have to know that we are always going to assume the hypothesis and arrive to the conclusion. This is what they're saying. And they say we're going to be doing this by using some idioms, definitions, rules, or logical inferences. Previously proven theorems. When we talk about logical inferences, we're talking about logic laws. We saw in this chapter we have what we call logic laws, which is when time permits, we can look at them. So we're given the first example. Check the first example, what they say. They say that use the direct proof to prove that if, you see, the statement will be given like this, it should be a conditional statement. If n is an even integer. So I'm just going to highlight n being an even integer. All right. And if n is an even integer, then n squared is also an even integer. So this will be labeled as our P. This will be labeled as our Q. You see right now. And this is the same in this format. P implies Q because it says if, then. And we're going to write, you need to write this. This is very important. You say, right, you need to write proof. Before you prove this statement, you need to write proof. You're going to write proof. Then you say P such that you put your P. This is your P. This statement here. N is an even integer, or n is even integer. Then Q, you're going to put n squared is also, I can't write the word also, we don't need this word also, right? We know that n squared is even integer. So you don't write things like also, you say right now, n squared is even integer. So let's see. Then we see what we do from there. You see, they say what Q, n squared is even integer. Then they tell us this. They say we need to assume P and deduce Q. So this is not what we are going to write. We are not going to write this. We are not going to write this. You say right now, that is not very important. They were just telling us. What we are going to write is this. You say right. This has marks and a lot of them. So first, if we go back, we see that our hypothesis is this, which in this case the hypothesis says that p is n is even integer. You see, right? So you're going to assume like this. You're going to say assume n is even integer. After assuming n is even integer, you need to show us what do you mean by even integer. You must write now, when I say that n is even integer, I'm saying that n is equal to 2k. But what is k? That's why we come to the fact to write for some k element of an integer. You see, right? That's why now we come to, so it's like I'm defining this. First, I say that n is even integer. What do I mean when I say that n is even integer? I say that it means that n is equal to 2k. And I came again and said, now I introduced k. What is k? I said for some k element of integer. This word for some is very important. If you just write for k element of an integer, you are wrong, because this might not be true for all numbers of k, but for some it can be. You see, that's our assumption. We are saying for some it will be possible. So now we'll understand why did we say we assume n is even. Then ourselves, let's make sure we even include the integer here right now. It's even integer. And then what do we mean when we say that n is even integer? We are saying that n is equal to 2k for some k element of an integer. Then check. And then check. Remember, after then we come here now. You see, that's why after assuming, we need to write it then. This is very important also to show that now we are going to the conclusion. When I come to the conclusion, I have n squared. Now I must prove that n squared is also an even integer. You see, right now I must prove that n squared is also an even integer. The question is, how am I going to prove it? I must now start from n squared because I know what is n. Then I take n, plug inside n squared, and try to prove that I'm also going to get an even integer. So let's see. So we know that n is equal to 2k. So I'm just going to start from this n squared and see that this will be equal to this one. You can simplify it here. They just simplify it, but someone would have even written n squared is equal to, since we know n is 2k, we just square, and this would be 4k squared. And we are trying to check here. Whenever you get here after simplifying, you need to factor out the 2 always, and the only added number that will be allowed is 1. So if I have plus 3, this one should be changed to plus 2 plus 1, so that when I come here I can factor out the 2 here. I'm only allowed to have plus 1. I can't be allowed to have plus 3, plus 5. Those are odd numbers. You see, right? The only odd number that I'm allowed to have is plus 1. So if I had the 5 here, I was going to change this to 4 plus 1, so that when I factor out the 2 here, always you should factor out the 2. I can you see we're talking about an odd and even integer. Those ones are always 2 terms. This one is an even one. Then 2 times k plus 1, it's an odd one. You see, right now? So you should always factor out a 2. So here I'm going to factor out the 2k squared. Then I'm going to replace this 2k by some variable. You see here they used m, and they say after that you can say for or where. You can use for or where m is equal to 2k squared. And this, after that, after letting this be an equal, they say this is an element of an integer. What they're trying to tell us is that m is an element of an integer. So if you write this, you would be wrong. If you come here and say this, and then you say this. I know some they do this. Those who have consulted so far, you said, and then I corrected them to say that it's not supposed to be like that. You're supposed to keep it like this. Remember, whatever they use in your guide, you should always follow the steps. Then we say hence n squared is even. Then we deduce. You see, right? And then, yeah, I think now we can try to do one question together and see if we can get it correctly. So let's see. We can do this. We approach a tutorial according to what we have went through first. So we are given this. They say that n is odd integer, then n squared plus 2n is odd. So let me do this. I'm just gonna take this quick. So that I can move. I don't want to be going up and down, right? Then I can move on to the next one. Let me see. Yeah. So this is methods of proof tutorial 1. So yeah. So now the question, the first, okay, they say we should prove the following. They say prove the following using direct proof. And then they give us the first question. They say the first question, they say if n is odd integer. Sometimes they don't even say integer. As long as they say it's odd or it's even, you must always keep in mind that they're talking about integers. Then n squared plus 2n is odd. You see, right? Then we're going to prove this. First I said that when you prove, you must write proof. You see, right now you're going to write proof, then you assign statements. P will always be the first statement here. Can I please attend this one? So here we have to always assign this statement that comes before then, or that comes in between if and then to P. You see right now. So we're going to assign that to P. We're going to say that n is odd integer. And then Q will always be the statement that comes after then. Is this one. You see right now. N squared plus 2n. They say n squared plus 2n is odd. You see, they didn't tell us odd what, but we must write odd integer. Then after writing this, we are going to assume. So now we must assume. We assume the hypothesis. Always you're going to assume P with direct proof, right? Assume n is odd integer. After assuming n is odd integer, we must write what does it mean when we say n is odd integer. It means that n is also 2k plus 1. What is k? For some k element of an integer, saying that k is an integer. Then remember, after writing then I'm gonna write this and try to prove. And then n squared plus 2n is also, now I plug n on this one, I plug 2k plus 1 on n, 2k plus 1. After here, I'm gonna give you something to write, right? Make sure, guys, that you write it. I know sometimes it's difficult for you to study, but make sure you do write. You're left with a few days. If you can apply the work now, you'll thank yourself later. Then this will be why am I, this one is squared, and this is 4k squared plus 6k plus, is it 6k? Oh, I see, I made a mistake here. Let me do this. This one is, Let me erase it and resolve it again. And solve it again here. I don't know why did I make such a mistake. N1 squared 4k plus 1 plus 4k plus 2. So check here, right? I'm going to have 4k squared, right, plus 8k. And then the constants that I have here is 2 plus 1. I'm not going to add them because I need plus 1 at the end. You said if I was adding them, I was going to have a lot of steps. So don't add. Always have, as long as when you add them, they're not giving you an even number. Don't add them. Just leave them like this. You see, right? Then now I'm going to factor out the 2. This will be 2k squared plus 4k plus 1. Then I have plus 1 outside. So I should only have that outside. Km plus 1. Where or for, can write where, m is also 2k squared plus 4k plus 1, which is an element of an integer. Then we saw that our conclusion said that this is what is odd integer. Then we have to now deduce and say that hence n squared plus 2n is odd integer. You see, right? Now we have come up with that conclusion. Now we have tried this question, right? And then what we can do now, we can do this. We can go back to the slides. We look at the second example. And then you write the second question here. Right, let's go look at the second example. Look at the second example. Let's see the second example. The second example that we have, they say that if n squared, or if n is even and m is odd, then n plus m is odd integer, or n plus n an odd integer, right? Then what we should do here, we should consider this as p, this is q, this is r, because we're given 3 statements here. Say n is even integer, and this is this end. You see right now. And then they say m is odd integer. And then they say n plus m is odd integer. Now we come and write proof. Then we assign statements. P is n is even integer. Then q is m is odd integer. Then r is n plus m is odd integer. Then I come to assume these two. I get the hypothesis. You see, anything that is in between if and then is what I'm going to assume. Now I assume that n is even integer, and it's like I'm just copying that and paste here. Assume n is even integer and m is an odd integer. Then I show what do I mean. When I say that n is an even integer, I'm saying that n is equal to 2k. And when I say that m is an odd integer, I'm saying that m is equal to 2r plus 1. Now, the reason why I want to consider this example before I give you that one to write is because if we check here, we've used k as a constant, but on the second one we can't use k because we've already used it. You see right now? So now from here, we are going to say what is k and what is r. So we're going to say for some k are element of an integer. After that we say then. After saying then, now we take our conclusion. Let me erase the other ones so they don't confuse you. Alright. After that, we now take our conclusion. After writing then, we take the conclusion, which is n plus m, which is this. Then I plug them there. I plug 2k plus 2. I plug 2r plus 1. Then I simplify them. I'm going to have here 2k plus 2r plus 1. This has a common factor of 2. I factor it out. Then I replace k plus r by a q. I can't use m because I've already used it, right? You can't use something where you've already used it. Then I say for or where q is equal to k plus r, element of an integer. Then hence indeed this is an odd integer. You see, right? The reason why it's an odd integer is because we have plus 1 there. You see, right? So what you can do now, I think we should do this. What you should do now, you should write this. I'm going to expect everyone to send their solution. Means that if you're not sending your solution, we're going to have a problem, right? Yeah, I think I've already written these things here. So let me say this. You're going to write this one, right? I'm even gonna screenshot it now, then I send it in the group. So you're going to write this. Let me just stop the recording, then I'll give you how many minutes? Should I give you 5 minutes or 7 for writing this? How many minutes should I give you?
7 is fine.
7, right? Yeah. So I'm gonna give you 7 minutes. Means that 3 minutes I'll be checking your mistakes, and then I correct you individually. And then we come back here to make a correction. Let's do that.